In this lesson, we're going to look at some additional rules for finding derivatives that will help you to find the derivatives of a wider range of functions than what you already know how to do. You should have already had the rules for finding the derivative of a constant, for a power, for a constant times a function, for the sum and difference of functions as well, and also probably the sine and the cosine function. We're going to look at an example that will illustrate why we need what's called the product rule for finding derivatives. Find the derivative of f of x equals 5x squared minus 3x times 2x plus 7. We do not have a rule right now that tells us what to do if we have one function being multiplied times another function. So what I'd like to illustrate for you using this particular function is something that you cannot do. For example, we can multiply these two functions together, can't we? Let's do that and rewrite our function. We're just going to use a FOIL process here. 5x squared times our 2x would give us 10x cubed. Our outside product, 5x squared times 7, would be a plus 35x squared. Our inside product is going to be a negative 6x squared. And finally, the last two terms multiplied is a negative 21x. Now I'm going to go ahead and simplify this before we find the derivative. We have 10x cubed. 35 minus 6 would give us 29x squared minus 21x. Now in this form, we can apply the rules that we already know and get the derivative. 3 times 10 would give us 30x squared, recall the power rule. And then we would bring the 2 down. 2 times 29 is 58, and we would have x to the first power. And then finally minus 21 times 1. So this would be our correct derivative. What I want to show you is something that you cannot do, but that students always want to do when they have a function written in this form. Notice that the derivative of this first function right here is 10x minus 3, and the derivative of the second function is 2. Notice if I multiply those, I have 20x minus 6. That is not the derivative of this function, is it? What I'm showing you is that if you have a product of two functions, you cannot take the derivative of the first one, take the derivative of the second one, and multiply those derivatives. It's just not that simple. What I do want to show you is an illustration of the way that you do have to find this derivative. Notice if I write down the first function, 5x squared minus 3x, and I take the derivative of the second function, which is a 2, I'm showing the first function written down like it is, and then the derivative of the second one being multiplied times that. Now I'm going to put an add here. I'm going to write the second function down exactly like it is. I'm going to take the derivative of the first function, which is 10x minus 3, and we're going to simplify this and see what happens. Multiplying here, I have 10x squared minus 6x, and then foiling these, 10x times 2x gives me 20x squared. I have minus 6x for the outside product, a plus 70x for the inside, and finally a minus 21. Let's simplify. 10x squared plus 20x squared is 30x squared. I have a minus 6x. Another minus 6x would be a negative 12x. Negative 12 plus 70 gives me a positive 58x. And then finally the minus 21. And you can see that these two answers are the same, and this is the correct answer. Now let's look at what we did. We took the first function exactly as it was written. We multiplied times the derivative of the second function, and then we added the second function, like it was written, times the derivative of the first one. That gives us what is called the product rule for finding a derivative. Notice if f of x and g of x are both differentiable functions, again that just means we can find their derivatives, then the derivative of their product, f of x times g of x, is given by the following. The derivative with respect to x of f of x times g of x equals f of x times g prime of x plus g of x times f prime of x. In this form, the product rule is sometimes a little bit hard to remember, and so I usually have my students learn this product rule in words. Let's look at it in words. The product rule says take the first times the derivative of the second plus the second times the derivative of the first. First times derivative of second plus second times derivative of first. If you'll memorize this product rule in words and you sort of say these words to yourself, then you're going to know exactly how to find the derivative when you see a product of two functions. Let's look at an example. Find the derivative if f of x equals x times the cosine of x. Now, I might caution you that I'm being very careful to read this using the word times. Most students look at this and they say f of x equals x cosine x. You need to learn to read it in your mind at least so that you're saying or thinking that word times, because when you say x times cosine x, you can see that you have a product of two functions, that word times indicating that we have a product. That's what indicates to me that we need to use a product rule here. Let's follow through the product rule. F prime of x equals first, our first function is x, times the derivative of the second function. The derivative of cosine x is negative sine x. Okay, first times derivative of second plus the second function, cosine x, times the derivative of the first function, 1. Okay, first times derivative of second plus second times derivative of first. Now we're going to simplify this. X times negative sine x can be written negative x sine x, and then of course we don't need that 1, so we can just say plus cosine x. Now I want to caution you here to be very careful to notice the difference between this problem that we just did and one that looks like this. I'm doing a times here, x times cosine x. I'm also doing a times here, 3 times cosine x, but what's the difference? Here I have a constant times the function, whereas here I have a function times a function. Do you see the difference? Both of these involve that variable x, so they're both functions. If they're both functions, the product of two functions, you use the product rule. If you have a constant times a function, then you just bring the constant down times the derivative of the function. So this one would just be negative 3 sine x. It's very important that you see and understand the difference between a product of two functions and a constant times a function. Okay, let's look at our second example down here. We want the derivative, y equals 3x times the sine of x plus 6 times the cosine of x. Well, you see your plus sign here. I have this function plus this function. Well, we learned that we take the derivative of this plus the derivative of this. So let's go back to this first one. You see this first one, however, is a product of this function times this function. This is what sometimes makes derivatives challenging. We are using the fact that we have a sum of two functions, but we're also going to be using the product rule here for the product of two functions. So for this part right here, using the product rule, first function 3x times the derivative of the second function, cosine x, plus the second function, sine x, times the derivative of the first function, 3. Now, all of this, let me just kind of underline, all of this is the derivative of this first part right here. Now we're here, so we're going to add the derivative of this second part. Here I have a constant times my function. So I'm going to bring down my constant, and the derivative of cosine is negative sine x. Now let's simplify this. I have 3x cosine x plus 3 times the sine of x minus 6 times the sine of x. Now these two terms ended up being like terms, and so I can add those together. 3x times the cosine of x, and I'll have minus 3 times the sine of x. Now you can leave your answer like this, that's fine. Sometimes, however, you will see in some texts that they might factor that 3 out and write the final answer like this. Either of these last two forms is an acceptable form for the answer. So we've illustrated here if we have a product of two functions, first times derivative of second plus second times derivative of first. If you have a constant times a function, it's the constant times the derivative of the function. And of course here we're using the fact that we're adding functions, but inside there we also have a product. Alright, well let's look at this one. Find the derivative. And we have 3x squared plus 2x all divided by x. Again, until now we have not had a rule that tells us how to do this derivative. So again, I want to illustrate what not to do, sort of. I'm going to rewrite this function. In other words, I can divide x into both of these terms. X into 3x squared gives me 3x, plus x divided into 2x gives me a 2. Notice if I actually divide that out and write it like this, the derivative is just going to be a 3. What I want you to see again is what not to do. Here's what students always want to do. They want to look up here and take the derivative, which would be 6x plus 2, and then look down here and take the derivative and get 1. But does this equal this? Those are not equal, are they? So you can't do that. You can't take the derivative of the numerator and the derivative of the denominator and just leave it like that, because that's incorrect. Again, we're going to look at what's called the quotient rule. We're going to come back and find this derivative using the quotient rule and show you how that works. If f of x and g of x are both differentiable functions, the derivative of their quotient is given by the following. The derivative with respect to x of function f divided by function g equals g of x times f prime of x minus f of x times g prime of x. All of this is over g of x squared. And of course over here they're telling you g of x can't be 0 because it's down here in the denominator, and we cannot have a denominator of 0. Now we're going to just follow this process with our previous example, and then we're going to learn how to learn this rule a little bit easier than this complicated formula. But let's look at this. G of x, where is that? That's our denominator. So for this function, according to that quotient rule, we would write the function down that's in the denominator, okay? The one that's on the bottom goes right here. And then we're going to multiply it times the derivative of the one that's up here. Well, our derivative up here is 6x plus 2. Then you'll notice it says minus, subtract. Then it has f of x. F of x is the function on top. For us, that would be 3x squared plus 2x times g prime of x. G is the one on the bottom. The derivative of the one on the bottom here for us is a 1. And then finally it says g of x squared, the one on bottom squared, x squared. Let's simplify this. I have 6x squared plus 2x, distributing my negative, minus 3x squared minus 2x, all divided by x squared. Well, 6x squared minus 3x squared is 3x squared. Notice the 2x minus 2x drops out. So we just have 3x squared over x squared, which is a 3, which gives us our correct answer. Now, obviously, we would not want to do this problem this long way when it's so easy to rewrite it like this and get the derivative. But we simply use this to show you what you cannot do, the thing everybody wants to do, but that just does not work because it does not give you the correct answer. But let's do here the same thing that we did on the product rule. Instead of learning the quotient rule through this, we're going to learn it in words. In words it says denominator times derivative of numerator minus numerator times derivative of denominator, all of this over denominator squared. Do you see, looking again back at here, denominator times derivative of numerator minus numerator times derivative of denominator over denominator squared. Again, the reason that I'm suggesting that you learn this in words is because if you say these words to yourself, then as you say the words, you're telling yourself how to find that derivative. And it's so much more meaningful in words than it is in those symbols. Let's apply the quotient rule to this problem. Now notice this one would not be so easily rewritten as the first example that I did. It would be very difficult for us to divide 7 minus 4x into this polynomial up here. So the easiest way to get this derivative is to use that quotient rule. So we're going to say the words and do this together. It starts out denominator. Denominator is the one down here on the bottom, 7 minus 4x. Denominator times derivative of numerator. The derivative of the numerator is 6x minus 5. Denominator, derivative of numerator, minus numerator, 3x squared minus 5x plus 1 times derivative of the denominator. The derivative of this denominator would be negative 4. All of this is over the denominator squared. Now, I grant you that is sort of a mess and you have to simplify it, but it's the only way that we can get the derivative here. Okay, we're going to simplify this out. So we're going to FOIL here. 7 times 6x is 42x. The outside product is negative 35. Inside minus 24x squared. Last two, positive 20x. Now, let's be careful here. The negative 4 times this, and then I've got this minus here. We can just change those signs, can't we? A negative times a negative. That'll be easier, and then we distribute that 4. So we have a positive 12x squared minus 20x plus 4. All of this is still over 7 minus 4x quantity squared. Now let's see if we can get our like terms. Negative 24x squared plus 12x squared. Let's add those two together. We'll get negative 12x squared. Okay? Now I notice here's a plus 20x and a minus 20x. Let's get rid of those. So we have a positive 42x left, and we've taken care of that one. We should just have constants. Negative 35 plus 4 is a negative 31. That's over 7 minus 4x quantity squared. Now, usually we do not square this part out here unless there's some reason that you particularly want to do that. Usually we'll just leave that in this form right here. There's not anything that we can do here to simplify this farther. So at this point we've had that product rule, first times derivative of second plus the second times the derivative of the first. We've also had the quotient rule, denominator times derivative of numerator minus numerator times derivative of denominator, all over denominator squared. I would suggest that you really work on memorizing those two rules using your words. Now, we want to prove the power rule for negative exponents. In other words, the derivative with respect to x of x to the n power is n times x to the n minus 1 if n is a negative number. Well, let's do this. If n is negative, then minus n is positive, isn't it? The opposite of n, if n is negative, the opposite of n would be positive. Let's just use a different, let's say p equal the opposite of n. P then is positive, isn't it? Right? Okay, so if I have x to the n, this would equal 1 over x to the negative n, right? Because if you move it down, this exponent changes sign. And then we're going to put a p in place of that negative n. So I'll have 1 over x to the p, okay? If I want the derivative with respect to x of 1 over x to the p, remember this is positive, I'm going to use my quotient rule. Denominator, x to the p, times the derivative of the numerator, well, the derivative of 1 is 0, minus the numerator 1 times the derivative of the denominator. If that's a positive exponent, we know we bring it down, x, and we subtract 1, don't we? All of this is over the denominator squared. Well, let's take a look at this. X to the p times 0 would just be 0. So I have minus p x to the p minus 1 over x to the 2p, right? Okay, well, let's do this. If I bring this up, I've got minus p x to the p minus 1 times x to the negative 2p. We have the same base, so if we add these exponents, p minus 2p is a minus p minus 1, okay? If p equals negative n, then minus p equals n, doesn't it? So I'd have n x to the n minus 1. And I've shown that that power rule also is true for negative exponents. I want to look at these two examples because I want to talk a little bit about how to know when you absolutely have to use that quotient rule and perhaps when you don't. Here I want you to notice that I do have a quotient, but down here in the denominator 4 is just a constant. This function I'm going to rewrite as 1/4 times the quantity 5x cubed minus 2x squared. This is the same thing. But I now have a constant times a function, and so if I want to get the derivative, I just bring my constant 1/4 down, take the derivative of my function, 15x squared minus 4x. And then if you want to rewrite that as 15x squared minus 4x over 4, you can do that. Now the difference is, even if I wrote this as 1 over 5x times the quantity 4x squared minus 9, I would not have a constant, would I? On this one, the most efficient way is to use the quotient rule. Since I have a function divided by a function instead of a function divided by a constant. That's the difference. Here we're going to use the quotient rule. Denominator times the derivative of the numerator, which would be 8x, minus the numerator, 4x squared minus 9, times the derivative of the denominator is a 5, all divided by the denominator squared. Okay, let's simplify. 5 times 8 gives me 40x squared, and I'll have a minus 20x squared. Do you see that? The 5 times the 4x squared times with the minus, and then I'll have a negative 45, but minus that will make a plus 45 over 25x squared. And then finally, we'll simplify there. We have 20x squared plus 45 divided by 25x squared. We can factor a 5 out of the numerator, 4x squared plus 9. And then that will allow us to cancel the 5 with the 25. And finally, we'll have 4x squared plus 9 over 5x squared. I wanted to illustrate the difference between a function divided by a constant, which is more easily done as the constant times the function rule. Whereas if you have a function divided by a function, the best way is to go ahead and do the quotient rule for your functions. Well, let's look at this one. F of x equals 1 over x minus 5x divided by 3x plus 2. The first thing I notice is that it is a function divided by a function, so the quotient rule is appropriate, but it's very complicated. So what I would recommend is before we do the quotient rule here, let's simplify this a little bit. This is a complex fraction. So let's simplify our complex fraction a little bit by multiplying numerator and denominator both by x. X times 1 over x gives me 1, and then I'll have minus 5x squared. Do you see that? And then down here we will have 3x squared plus 2x. The quotient rule applied here will be much easier than the quotient rule applied here, where even if you write that as a negative power, it's going to be very difficult. So let's apply the quotient rule. Denominator 3x squared plus 2x times the derivative of the numerator, negative 10x, minus the numerator, 1 minus 5x squared, times the derivative of the denominator, 6x plus 2. All of this is over the denominator squared. Sometimes I have students forget this part. They'll do this part and they'll forget over denominator squared, and you're going to lose a lot of points if you forget that part. So learn to say the rule, and as you are checking yourself, are all the parts there? Denominator, derivative of numerator, minus numerator, derivative of denominator, over denominator squared. After you do a few of these and say that formula, you should have it memorized. Okay, let's simplify. We'll distribute our negative 10x. So we have negative 30x cubed minus 20x squared. Now I'm going to caution you here, let's be really careful. I've got this minus sign, and these are binomials, so let's bring our minus down and let's use a bracket here. We have a 6x. The outside product is a plus 2. Inside we have a minus 30x cubed, and the last 2 gives us a minus 10x squared. If you'll do it like this, you won't tend to make those careless mistakes with your signs that I see so often. Okay, to save having to rewrite this, this negative would make this a negative 6x, a negative 2, a positive 30, and a positive 10. Do you see that? So I have a negative 30x cubed here, and a positive 30x cubed here is going to drop out. Negative 20x squared and plus 10x squared gives me negative 10x squared. That takes care of that term and that term. And finally, I have the minus 6x minus 2, all divided by 3x squared plus 2x quantity squared. Okay? I distributed that negative there and changed those signs. Now, if you would like, you could, of course, factor a negative 2 out of this numerator. That would leave 5x squared plus 3x plus 1. Nothing will cancel, but sometimes we do see the final answer written in that form. But I just wanted to illustrate, sometimes before you just start writing on a derivative, you may want to look at your original function and see if you need to maybe simplify first and put it in a different form. Let's move to some trig function problems. Find the following derivatives. Y equals the sine of x divided by the cosine of x. Notice the quotient of two functions. Well, let's see. We have denominator, whoops, let me not put equal, but let's put y prime. Denominator cosine x times the derivative of the numerator. Well, the derivative of sine x is cosine x, minus the numerator, sine x, times the derivative of the denominator. Well, the derivative of cosine is negative sine x over denominator squared. I'm going to write it that way, cosine squared x. Well, let's see, if we simplify, we have cosine squared x, multiplying these, negative times a negative is plus sine squared x over cosine squared x. Well, do you remember your trig? Cosine squared x plus sine squared x, that's 1, isn't it? So we have 1 over cosine squared. 1 over cosine squared is the same thing as secant squared, isn't it? That's interesting. We're going to come back to this in a second. Let's look at this one. This time we have cosine x over sine x, and we're going to get the derivative. Denominator, sine x, times derivative of numerator, negative sine x, minus numerator, cosine x, times derivative of denominator, cosine x, all over denominator squared, so that's sine squared. So I have negative sine squared x minus cosine squared x over sine squared x. Well, if I factor out a negative, negative sine squared x plus cosine squared x over sine squared x, again using your identity, that's negative 1 over sine squared x, or negative cosecant squared x. What is sine x over cosine x? Isn't that tangent x? And cosine over sine is cotangent x. I think we've just shown here that the derivative of tangent x is secant squared x, and the derivative of cotangent x is negative cosecant squared x. We proved it using the quotient rule, didn't we? We'll put this on a screen for you in a second, and I will recommend that you memorize those. But let's look at these functions. Y equals cosecant x. Cosecant is 1 over sine. If I use the quotient rule on this, denominator sine x times the derivative of the numerator, derivative of 1 is 0, minus the numerator times the derivative of the denominator, that's cosine x, over denominator squared. Well, of course, sine x times 0 is a 0. I have minus cosine x over sine squared x. Let's write that like this. Minus 1 over sine x times cosine x over sine x. See, that's still minus cosine over sine squared. Let's bring down the negative. 1 over sine is cosecant. Cosine over sine is cotangent. The derivative of cosecant x is negative cosecant x cotangent x. I think you can see where we're going. Secant is 1 over cosine. So using the quotient rule, denominator cosine x, derivative of numerator 0, minus numerator 1, derivative of denominator is negative sine x, over denominator squared. So again, that's 0. A negative times a negative gives me positive sine x over cosine squared. I'm going to write that as 1 over cosine x times sine x over cosine x, sine over cosine squared. So I have 1 over cosine is secant x, and sine over cosine is tangent x. So the derivative of secant x is secant x tangent x. We have just shown the derivatives of the other trig functions. Remember, we already knew that the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Now we know the other 4. The derivative of tangent x is secant squared x. The derivative of cotangent is negative cosecant squared x. The derivative of secant x is secant x tangent x. and the derivative of cosecant x is negative cosecant x cotangent x. Something interesting. The derivative of sine x is cosine x. Sine, tangent, secant all have positives in their answer. The derivative of cosine x, cotangent x, cosecant x, and in other words, all the cofunctions, those all have negatives in front. That might help you to remember which ones get the negative. You'll need to memorize the rest of these formulas so that you can use them. Find the derivative f of x equals 3x squared plus 2 tangent x. I have a sum of these two functions, so I will use the rule that we do the derivative of the first one plus the derivative of the second one. The derivative of my first function using the power rule, 6x, plus I have a constant times this function, I'll bring the constant down, times the derivative of tangent x. We just showed that the derivative of tangent x is secant squared x. So we have 6x plus 2 secant squared x. About all you can do to that, if you want, is to factor a 2 out and perhaps write it like this. Again, either of those answers would be a good form to leave that in. But notice how easy it is to get this derivative if I just know that the derivative of tangent is secant squared, so that I don't have to rewrite that as sine over cosine and use that quotient rule to get there. Find the derivative y equals 1 plus sine x over cosine x. Actually, I want to show you two different ways to do this derivative, and you can choose which way you might think is easier, but I also want to show you that sometimes, depending on how you approach the problem, you may get an answer that looks a little different than someone else's. If we leave this like it is, 1 plus sine x divided by cosine x is a quotient of two functions. So if I just simply follow the quotient rule here, let's take a look at it. Denominator cosine x times derivative of the numerator, 0 here, derivative of sine is cosine, so that would be cosine x, minus the numerator, 1 plus sine x, times the derivative of the denominator is negative sine x. All of this is over denominator squared, cosine squared x. Okay, let's simplify. I have cosine squared x here. Now let's be careful. This negative and that negative will cancel each other out. So I'll have a sine x plus sine squared x over cosine squared x. Cosine squared x plus sine squared x is a 1. So I can simplify this to 1 plus sine x over cosine squared x. And that looks pretty good, doesn't it? Okay, well, let's look at this another way. If I split this up as 1 over cosine x plus sine x over cosine x, do you see what I'm doing, dividing cosine into both? 1 over cosine is secant, and sine over cosine is tangent. Let's look at the derivative in this form. The derivative of secant x is secant x tangent x. And the derivative of tangent is secant squared x. So, boy, that's pretty easy, isn't it? Secant x tangent x plus secant squared x. But look how different these look. Let's just see if we do have the correct answer in this form, even though it looks so different from this one. Let's look at this just a little bit in terms of simplifying. First of all, notice I could factor out a secant x, which would leave a tangent x plus a secant x. Secant is 1 over cosine, isn't it? Tangent is sine x over cosine x. Secant is 1 over cosine x. So I have 1 over cosine x, and in here with the same denominator, I can say sine x plus 1 over cosine x. And then finally multiplying this, I have sine x plus 1 over cosine squared. And you can see that these are equivalent. Now, is this an okay answer? Yes, it is. It's certainly correct. Is this an okay answer? Yes, it is. I just warn you that depending on how you chose to do the problem, perhaps you saw this and you were checking your answer in the back of the book and maybe they had this. Don't assume always that you've necessarily done it wrong. Now, you perhaps could have made an error, but sometimes, particularly with these trig functions, depending on how you approach it, you might get answers that look different, but in fact, using identities, you can show that they're exactly the same. Okay, let's look at this one. Find the derivative y equals x cubed times the cosecant of x. Notice I have a product of two functions here. So we're going to be using the product rule here to get this derivative. First function x cubed times the derivative of the second function. The derivative of cosecant is negative cosecant x cotangent x. First times derivative of second plus my second function is cosecant x times the derivative of my first one, 3x squared. Now again, remind yourself to say it and make sure you have all the parts. Some students quit too soon. First derivative of second plus second derivative of first. Now let's simplify this. I have negative x cubed cosecant x cotangent x. And be careful here, this 3x squared is times your cosecant. It's not times the x. So let's put that 3x squared in front to make that absolutely clear. So I have 3x squared in front of the cosecant. Now, if you want to do some factoring here, you could factor out x squared, you could factor out a cosecant, you could also factor out a negative if you want to. I think I'm going to do it that way. I'm going to factor out negative x squared cosecant x. So I would have an x times a cotangent here. Notice if you multiply these, you get your negative cosecant cubed, negative x cubed cosecant x cotangent x. And then minus 3 would give you your plus 3x squared cosecant x. That's about all you can do in terms of simplifying this one. Now, we're going to look at some problems that are asking us for the second derivative. Now remember, that just means we're going to have to go through the first derivative first and then get the second. This function is being divided by this function, so I need to use a quotient rule here, don't I, to get the derivative. Now remember, I'm doing first derivative right now. Denominator 5x. Derivative of the numerator, 2x minus 3. Minus the numerator, x squared minus 3x plus 2 times the derivative of the denominator 5. All of this is over the denominator squared. Let's simplify. I have 10x squared minus 15x, and negative 5 distributed here will be a minus 5x squared plus 15x minus 10. Did you follow that? 5x squared negative. Negative 15x with a negative is a plus, and 10 with a negative is a minus 10. All of this is over 25x squared. Well, let's see. Let's keep going here. 10x squared minus 5x squared gives me 5x squared. Minus 15x plus 15x drops out, minus 10 over 25x squared. Well, we can still do a little simplifying, can't we? Let's factor a 5 out of the numerator. Gives me x squared minus 2 over 25x squared, and then we can cancel the 5's. X squared minus 2 over 5x squared, okay? That's just the first derivative, isn't it? So, to get our second derivative, we need to take the derivative of this one. Notice I got it as simple as I could before I start in again, because I'm going to have to do a quotient rule a second time. Denominator, 5x squared, times derivative of numerator, 2x, minus numerator, x squared minus 2, derivative of denominator, 10x. All of this is over my denominator squared. You with me? Now, let's see about simplifying this one. Let's see, we've got 10x cubed minus 10x cubed, you see that one, plus 20x over 25x to the fourth power. My 10x cubes drop out, 20x over 25x to the 4th. Well, let's see, 20 and 25 can be divided by 5, and the x will cancel, and so I'll have 4 over 5x cubed. Let's find the second derivative, and we're given f of x equals cotangent x over tangent x. Now, that looks like we would have to do a product rule to get our first derivative. But before you go to a lot of work, I want to caution you on these trig functions. Sometimes you can save yourself a lot of work if you look at it ahead of time. Notice that the cotangent of x is cosine x over sine x. The tangent of x is sine x over cosine x. These cancel, so that's just 1. Cotangent x times tangent x is 1. That's just a constant. That means the first derivative is 0, so is the second one, because the derivative of any constant is 0. Now, if you recognize that, that's extremely easy. If not, you're going to go all through this product rule, first times derivative of second plus second times derivative of first. It will be interesting to see if you do that. Would you come out with a 0? Let's just kind of run through that the hard way and see. If we use the product rule, first function cotangent x times the derivative of tangent is secant squared plus the second function tangent x times the derivative of the first, the derivative of cotangent is negative cosecant squared. Well, goodness, cotangent x times secant squared x minus the tangent of x times cosecant squared doesn't really look like 0 yet, does it? But let's look again. Cotangent is cosine x over sine. Secant squared is 1 over cosine squared. Tangent is sine x over cosine x. Cosecant squared is 1 over sine squared x. Your common denominator would be sine squared x cosine squared x, wouldn't it? So you'd need to multiply this by a sine x over sine x. So you'd have sine x cosine x here. And this one you'd need to multiply by cosine x cosine x. So you have minus sine x cosine x over cosine squared x sine squared x. Finally, you can see that will add to 0. But what a lot of work that you don't have to go through if you recognize up front that that's just a constant function. That's kind of tricky, isn't it? Okay, well, let's do an application problem here. Find the equation of the tangent line if f of x equals the tangent of x and x equals pi over 6. Well, remember, the derivative gives us slope, doesn't it? So the derivative of tangent x we learned is secant squared x. This is our formula for slope. So our slope will be secant squared x is pi over 6. Now, if it's been a long time since you've done trig, pi over 6, remember, is like 30 degrees. So if you remember your 30-60 triangle setup, and remember that the secant is 1 over cosine. So this is like 1 over cosine squared pi over 6. It's the reciprocal of the cosine. The cosine of 30, cosine of pi over 6 is square root 3 over 2. Okay? So that means that the secant of pi over 6 is 2 over the square root of 3. And so if you square that, you're going to get 4 over 3, aren't you? So m is going to be 4/3. Now, your formula, y minus y1 equals m times x minus x1. We have figured out m is 4/3. We know our x1 is pi over 6, but what we're missing is what about y1? Y minus what? Well, remember, f of x just means y. So to find our y1, it's going to be the tangent of pi over 6. The tangent of 30 is 1 over the square root of 3. Or if you rationalize that, square root 3 over 3. So this is y minus square root 3 over 3. And then we can simplify this if we solve for y. Let's distribute that 4/3. 4/3 x minus 4/3 times negative pi over 6. We're going to get, let's see, 2 pi over 9. I'm trying to reduce that as I do. 4 and 6 have a common factor of 2. So you get a 2 here and a 3 here. It gives us our 2 pi over 9. And then this would be added over here plus square root 3 over 3. Now, there's not really any good way that we can combine those without going to a calculator approximation. But I just want you to understand, here's your m right here. And this quantity right here is basically your y-intercept, whatever that would simplify to. But we have the equation of the tangent line at x equals pi over 6. This concludes our lesson on the product and quotient rule. I spent probably more time on the quotient rule simply because it's so much more complex than the product rule, and students have a lot more trouble with that. But again, I caution you, memorize those formulas in words so that you can work your problems saying the formula and basically telling yourself what to do. And then it's just a matter of simplifying. And of course, you are going to need to spend some time to memorize those trig function formulas. This completes your lesson on product and quotient.